In this video, we are going back to calculus. So we are going to be discussing conic sections, what they are, how to find them or how to create them, what they look like in equation form, and how to work with them. So what exactly is a conic section? Well, it's the curve of intersection between two surfaces, where the one surface is a cone and the other surface is a plane. So you can sort of think of it as the plane slicing through the cone at a specific angle. And the curve that we get when slicing through the cone, that is going to be our conic section. Now, if we change the slope of the plane, we also change the curve that we get out. So we will be looking at three different curves of intersection. The first will be giving us a parabola, the second will give us an ellipse, and the third is going to give us a hyperbola. I'm going to show you just a quick animation of what is actually happening as we change the slope of the plane. But you can see on the figure to your left that if the plane is quite steep in this case, it looks like we are getting two branches of a hyperbola as our curve of intersection. You can copy that link or you can click on it. It will take you to GeoGebra where you will see this exact animation. You can play around with the orientation of the plane and see what happens with the different types of curves that you will get out. So I'm going to play it now. It's starting with a hyperbola, and the plane is going to go slowly horizontally and then back up to vertical. And you can take a look at what happens with the curves as that happens. So at some point we get a parabola. Then when it goes horizontal, we will get an ellipse. It's going to go back up to vertical now. So again, at some stage, it switches over to a parabola. There we go. But at some point, when it gets too steep, we switch back to hyperbolas. Our first curve that we will be looking at is the parabola. So you guys at this stage know what the graph of the parabola looks like, you know what the equation looks like, and you know what each part of the equation actually represents. But where does the actual equation come from? Well, we define a parabola as the set of all points that are equidistant from a fixed point, which we will call the focus of the parabola, and a straight line, which we will call the directrix of the parabola. What are we looking for? We are looking for all points or all coordinates x, y, where our point is the same distance from or to the focus. So let's take this one. The distance to the focus will be the same as the shortest distance to the directrix. This first point is actually the exact midpoint between the focus and the directrix, so it makes sense. These distances are the same. I'm going to show you in the animation now how we build up or how we find all of these other xy coordinates and how it makes sense graphically. And then we'll take a look at how do we actually get the equation. So let's play this one. Let me quickly just get that. We are going to first move very slowly to the left. So change our x coordinates, make them smaller. And you can see, again, always the distance between our point and the focus is the same as the distance or the shortest distance from the point back down to the directrix. So if we have this and we put together all of those coordinates and we connect them, they will trace out the shape of a parabola. So let's derive our very first formula. We are going to keep things very simple. So for this one, we are going to look at a standard upward-facing parabola with the turning point at the origin. One nice thing about the turning point is we saw that it lies exactly between the focus and the directrix. So to show you here, if the turning point is at the origin, it means the focus and the directrix will lie exactly above, and well, the y-intercept of the directrix will lie exactly below our turning point, and these distances, according to the definition, have to be equal. So if we have our focus on the y-axis at some height p, and we have the coordinates 0, p, then our directrix will be at height negative p. So our directrix will have an equation of y is equal to negative p. And then we want to describe a point that lies on this curve. So if we have any random point, let's just call it xy, we know there are certain specific properties that xy have to satisfy in order for it to lie on the parabola. And that's what we are going to be using. So what we'll do first of all is we can calculate the distance between the focus and this point xy. We have a formula for that. But we need to also have a formula for the distance from xy down to the directrix. What will the coordinate of the point be if we project xy here perpendicularly down onto the directrix? Well, the x coordinate will be the same, but the y coordinate, because that point lies on the directrix, will be negative p. This is all we need to start. Firstly, we are going to describe the distance between the focus and our point on the graph using that distance formula. And this will be the square root of the difference between the x coordinates squared, which will be x minus 0 squared, plus the difference between the y coordinates. So in this case, y minus p squared. Then we are going to take a look. This has to be equal to the distance from our point to the point on the directrix. So this will be the distance from xy to x minus p, and this is also given by the square root of the difference between the x coordinates, in this case x minus x squared, plus the difference between the y coordinates. So here we have y minus p squared. Now all we need to do is we need to simplify. This is what describes what's going on our graph, on our curve, for that specific point xy. So if we can take this equation and simplify it to something nice, that is actually the equation that describes the parabola itself. Okay, so on the left, first thing that we can actually do is we have a square root equal to a square root. So let's get rid of the square roots and just square the left-hand side and the right-hand side. And then we can take a look at the brackets inside. X minus 0 squared will just give us x squared, and y minus p squared gives us y squared minus 2py plus p squared. On the right, we have x minus x squared, which is just 0. And then we have to square y plus p. This gives us y squared plus 2py plus p squared. A lot of things can cancel, luckily for us, in this equation. We have a y squared on the left, we have a y squared on the right. They can cancel each other out. We also have a p squared on the left and a p squared on the right. They can cancel each other out. And what is left, if we keep x squared on its own on the left, we get x squared is equal to 4py on the right. Now this is our standard equation for a parabola like this, cutting through the origin with a positive orientation or upwards, provided that p is positive. But this is also the same equation that will describe a parabola that is downward facing if p would be negative. So this is going to be our standard formula for a parabola that has its turning point at the origin. Let's take a look at our first example. We have to find the focus and the directrix of the parabola with equation x squared is equal to 8y, given the formula that we've just derived. Okay, so that's our first step. Where are we going to start? We are going to look at the standard form of a parabola, a vertical parabola specifically. So this is a parabola that either opens up to the top or to the bottom, but the turning point is at the origin. The formula that we've derived for a parabola like this was x squared is equal to 4py, where the p gives us details about the focus and the directrix. How do we know it's vertical? Well, we have this form. In our equation, we can always find a y is equal to x squared. Again, give or take a few coefficients, give or take a few signs, but y has degree 1, x has degree 2. If we see this, we know we are dealing with an upward or a downward facing parabola. Secondly, we know that our parabola hasn't been shifted. There are no other terms except for the term with x squared and a term with just y. If there are other terms, it means there could be vertical or horizontal translations as well. So for the moment, our turning point is at the origin, and how we derived this specific formula was that we saw our focus was along or on the y-axis, and the directrix was the same distance from the origin that the focus was. So in this case, our focus would be on the y-axis, so it would be at 0p. P gives us the height where the focus would be, and the directrix would then be y is equal to negative p. Same distance from the origin, but in the opposite direction as the focus. So now we take the standard form of the parabola and we compare it to the equation of the parabola that we were just given. So we have standard form is x squared is 4py, and this equation is x squared equal to 8y. So we compare the two coefficients of y. Everything else you can clearly see is the same. And if we compare them, we know that 4p must be equal to 8. So this is what we are going to solve. If 4p is equal to 8, it means p has a value of 2. And now we can plug it into what we know the focus and the directrix should be. We saw that the focus will be at 0p. So if p is equal to 2, our focus will be at 0, 2. And the directrix, y is equal to negative p. The directrix will have an equation of y is equal to negative 2. Now, just as we defined or how we derived the formula for a vertical parabola that has a turning point at the origin, we can do exactly the same for horizontal parabolas with turning points at the origin. The only difference is the vertical opens upwards or downwards, and the horizontal opens to the left or to the right. The equations look almost identical. For the vertical, we will have x squared is equal to 4py. And again, look out for this. Y is degree 1, x has degree 2. So that's our standard parabola that we've always been working with. The horizontal parabola looks almost exactly the same in its equation, but here y is squared and x has degree 1. This indicates that the parabola is lying on its side, so it's opening up either to the left or to the right. So for the first one, if we have some form of y is equal to x squared, again, give or take coefficients, signs, we have a vertical parabola. It opens upward or downward. But if we have this form x with y squared in the equation, we have a parabola that lies on its side. It opens up to the left or to the right, again, depending on the value of p. The turning point for the vertical, or this equation that you see on the left, is at the origin, and the same for the one on the right. Turning point is at the origin. If x is 0, then y will be 0, and vice versa. For the vertical parabola, the focus was on the y-axis, and we saw it is at 0p. Only difference for the horizontal is that the focus will now lie on the x-axis. So the focus will be at the coordinate p0. The directrix for the vertical was y is equal to negative p. So the only difference if we now flip it horizontally is that the directrix will have equation x is equal to negative p. Let's look at another example. Here we want to find the vertex, sometimes called the turning point of the parabola, the focus, as well as the directrix, and the equation is given slightly differently. Here we are dealing with 2x plus y squared plus 4 is equal to 0. We can try and again write it in the standard form that we've been using in this video, where the squared term is on its own on one side of the equation and everything else is on the other side. So let's start with that. let's say y squared must then be equal to negative 2x minus 4. Our standard form is y squared is equal to 4px. No other terms. So this extra term, the negative 4, could indicate a translation. So the graph could have been moved left or right, up or down. We need to see exactly how. So what we are going to do first is we are going to factorize what we have so that we can see directly which translations have occurred and where. So what I'm going to do here is I'm going to, on the right-hand side, factor out a common factor of negative 2. So this gives us y squared is negative 2, and what's going to be left in the brackets will be x plus 2. This is our actual translation. It means the parabola, in whichever form we have it, has been shifted 2 units in the opposite direction. So here we have x plus 2, which means our parabola has been moved 2 units to the left. All right, now let's compare and let's try and see what type of parabola are we looking at. The standard form, if we have a y squared, would be y squared is equal to 4px. Because we have an x raised to the power 1, but a y being squared, we are dealing with a horizontal parabola, or a parabola that's lying on its side. Depending on the value of p, this would be either a parabola that opens up to the right or to the left. But in this case, we don't just have y squared is equal to 4px. We have a translation as well, which we could show by this in brackets, x minus x 0. Now let's compare the formula that we have versus the formula that we have in the standard form. So we have that the coefficient of x is negative 2 in our equation, and in the standard equation, it is 4p. So here, first thing that we can do is we can find the value of p. So negative 2 must be equal to 4p, which means p is equal to negative a half. We can use this to find the focus and the directrix of the original graph before it was shifted, and then we can just apply the translation to find the actual focus, the actual directrix, as well as the turning point of this parabola. Let's put everything together. We tried to rewrite our equation in standard form as close as possible, and we got y squared is equal to negative 2 times x plus 2 in brackets. From this, we used the coefficient to calculate our p, and we saw that p is equal to negative a half. We are going to use this and the standard form of our equation to determine the vertex, the focus, as well as the directrix of the original untranslated graph, and then apply the translation to all of them. So we are going to take a look at the original on the left and the translated on the right. Remember the translation, because of the brackets x plus 2, means we are shifting our whole parabola 2 units to the left. So first, if we didn't have a translation, our standard form shows us a parabola that has its turning point at the origin. So the original vertex was at the origin at 0, 0. If we translate the vertex, it will move 2 units to the left. So it will be still on the x-axis, but at negative 2, 0. Next up, we need to find the focus. Well, according to our standard form, the focus is going to be on the x-axis at coordinates p, 0. Because p is equal to negative a half, our original focus was at negative a half, 0 on the x-axis. Just to recap, why is it on the x-axis and not on the y-axis? It's because we are dealing with a horizontal parabola, or a parabola that's lying on its side. We have some form of x with y squared, not y with x squared. So here we have a parabola that's lying on its side, and we have a negative p-value, which means it's opening up towards the left. So our parabola looks something like this. It's cutting at the origin, or it has its turning point at the origin. The focus will be inside the parabola, or at p0, which in this case is negative a half 0, and then the directrix will be the same distance from the origin, but in the opposite direction. So it will be at x is negative p. We'll take a look at that now. If our focus is at negative a half 0, and we want to translate it, meaning move the focus 2 units to the left, the new focus will be at negative a half minus 2, 0. Or if we simplify this, at negative 5 over 2 and 0. The directrix originally would have been at x is equal to negative p, or in this case, negative a half. So x is equal to a half was our original directrix. And again, if we apply the translation, we are going to move this directrix 2 units to the left. So we will now have a new directrix of x is equal to a half minus 2, which gives us x is equal to minus 3 over 2. This is our parabola, or this is what describes our parabola once it has been translated. So we can take the one in the sketch at the top, and we can just move everything that we see 2 units to the left, and we will have the parabola from our equation. What's important to take from this example is that we always use the coefficient of the term of degree 1 to determine, first of all, is it a vertical or a horizontal parabola, but then also to see in which direction does the parabola open up. Where will we find the focus? Because once we have the focus, we will be able to find the directrix. But in the case of this example, where there were extra terms that we didn't see in the original standard equation for the parabola that we are expecting, they could denote translations or shifts in our graph. And we have to keep that in mind once we have our focus and our directrix, to apply those shifts or translations to them so that we can have the new translated graph with all of its properties. One last thing that I wanted to mention that's very cool about parabolas is their reflective property. We spoke about the idea of equidistance, right? Any point on the parabola must be equidistant from the focus and the directrix. But parabolas also have this very cool property that if you have parallel rays, let's say parallel rays of sunlight, traveling towards a parabola like this. So these are all parallel lines. Once they meet the parabola, they reflect. Now, if they reflect, this is also sometimes called a parabolic mirror. Once they reflect or bounce off of the parabola's curves, all of these parallel rays of sunlight are pointing or reflected towards one central point, which is actually the focus of the parabola. Maybe that's why its name was given as focus. Another nice thing is if we have that at the focus, we have a source of light. So if the situation was reversed, and at the focus, we have rays of light now moving away from it towards the parabola, the same thing would happen, or the same paths would be followed. The ray of light would move towards the curve. At the curve, it would bounce or reflect off, and all of these rays of light would move away from the parabola in parallel rays. So this is something that's used in car design, in design of headlights, which I think is a pretty cool application we never really get to see with doing just the pure mathematics. But in the consequent videos on ellipses and hyperbolas with the conic sections, we actually have really nice applications that you can take a look at. Right, so this is it for this video. We are only doing the basic parabolas in this one. Next up, we will take a look at ellipses and then hyperbolas, and then we'll also do a couple of videos with more complicated examples on all three of these conic sections.